What comes to your mind when you hear the word energy? If you're like me, you're probably thinking, well, I need a soda or a coffee right now to keep me awake and to keep me energized to continue studying material and energy balances. Or maybe you think about our energy consumption, a gallon of gasoline, or maybe the sun beaming down on a lawn or on a plant in order to grow food. Or maybe you think about a battery providing energy to a piece of electronics. Or maybe you think about a person working out in a gym, on a treadmill, or on a stationary bike. While these are all definitions of energy that we know from everyday life, you ever stop to think about what exactly is energy? In other words, we know that the textbook definition of energy, most of you could probably recite it by now, and probably some of you right now are saying energy is just the ability of something to do work. But that's the textbook definition. Could you actually define it in a more tangible sense? What does it mean to have energy? What does it mean to use energy? What does it mean to transform energy? This is something that we know about energy, that it cannot be created nor destroyed. But how does one get it? How does one use it? Where does it go when it's done? These are all questions that I think about that I really don't think we have good answers for. But it gets us thinking about what is this energy topic. With that intro, we're going to start the second half of the class. This is officially chapter 7 in the Felder, Rousseau, and Bullard textbook. And also the second half of what we know as material and energy balances. So today we're going to start energy balances. And just like before, it doesn't mean that material balances are finished. It just means that energy balances we're going to start to consider on top of material balances. Let's start with that thing that I just mentioned, that we know already that energy cannot be created nor destroyed. What does this mean for our purposes? If you've picked up on my hints, we're going to start doing energy balances. And just like a material balance, the general form of any type of balance is in plus generation minus output minus consumption equals accumulation. If energy cannot be created nor destroyed, this means that generation is equal to consumption, which is equal to 0 for energy. So already our energy balance is going to be simplified. Before we talk about closed system or open system energy balances, which will be the topic of the next video, let's talk about the types of energy that you probably already know about. We'll start off with the ones from physics class. This is your P and K. I'm giving you a hint. What types of energy do you know of that start with the letter P or that start with the letter K? The first thing I'm thinking about is kinetic energy. Kinetic energy is due to translation of the system, so something moving. So when I think of kinetic energy, I think of a football running back running through the line, or I think of my pressure washer outside washing my driveway, or I think about a semi-truck rolling down the freeway. These are all systems that are moving and therefore possess a certain amount of kinetic energy. The formula for kinetic energy is well known from physics classes. And I'll also share that the term that we are going to use in MEB is E sub K. So E for energy, sub K for kinetic. You can probably all recite this formula, 1/2 mv squared, except in the Felder, Rousseau, and Bullard textbook, they call U velocity instead of V, which has another meaning. M is also mass, and you can also define a flow rate of kinetic energy by saying it is 1/2 the mass flow rate times the velocity squared. So that example I was just talking about the pressure washer, that water has a certain amount of kinetic energy. You can discuss the amount of kinetic energy that any fluid has flowing through a pipe. And sometimes, if it's like a hydroelectric plant or something, that kinetic energy can be transformed into different types of energy. Let's do just a very brief example of water flowing through a 4-centimeter inner diameter pipe at 10 liters per second. If we want to know what the velocity is, we have the volumetric flow rate here. I can write the formula that U, the velocity, is equal to the volumetric flow rate divided by the area that it flows. I know that the volumetric flow rate is 10 liters per second, and I can calculate the area of this water. So the formula for area of a circle is pi times r squared, and I'm going to convert to meters. So 4 centimeters is 0.004 actually, and half of that would be the radius. So 0.02 meters squared. I'm going to convert liters to meters cubed. So there are 1,000 liters per 1 meter cubed. And this is going to give me 8 meters per second, roughly. My mass flow rate is the amount of mass. So I have to convert this volumetric flow rate to a mass flow rate. So 10 liters per second. I know the density of water is 1,000 kilograms per meter cubed. But I also know that there are 1,000 liters in 1 meter cubed. So 10 liters of water per second is equal to 10 kilograms. If you ever want to just quickly double check, you know what a liter is approximately. So when I think of liter, I always think of 2-liter soda bottles. So imagine holding 5 soda bottles all at once. How much would that weigh? It would weigh about 25 pounds, which seems about right, which would be 10 kilograms. So that's a way that you can quickly just double check if what you're doing makes sense. So the kinetic energy of this system is 1/2 m, which is 10 kilograms, times 8 squared meters per second equals 640 joules per second, or the unit of energy transfer could be a power, 640 watts. So imagine, try and build an intuition for, is this a lot of energy? And 640 may seem like a large number, but remember that light bulbs can be 40, 60, or 100 watts. So this is about 10 light bulbs worth of energy. If I had water flowing through a 4-centimeter inner diameter pipe at 10 liters per second, first of all, 8 meters per second is pretty fast for the water to be flowing through. Also, 10 kilograms of water per second is a decent amount. So this seems like it'd be a lot of energy, but it actually isn't that much energy when you compare it to a light bulb. The second form of energy, which is no doubt familiar to you, is potential energy. And this is energy due to position within a potential field. When I say potential field, I mean gravitational, magnetic, or electromagnetic. And for this class, we're only going to talk about gravitational potential fields, not magnetic. You know from your physics class that the formula for potential energy, the variable for this is E sub P, is mgz, where m is the mass, g is the gravitational constant, and z is the height above a reference point, which is arbitrarily defined as having 0 potential energy. I need to write that point down because it's very important. So it's easy to remember a WWE wrestler, for example, climbing up to the top rope and gaining some amount of potential energy. However, say that I am in my office on the 3rd floor of Black Hall, and say I wanted to calculate how much potential energy that I have. Well, it depends on whether or not you set the reference state equal to the floor or equal to the ground outside. What would my potential energy be? What if I lived in Denver, which is a mile above sea level? Would my potential energy be relative to the sea or relative to the local ground level? This is a question that you have to answer. So it doesn't make any sense to say that a potential energy level is an absolute value. It's always relative to something else. And it can be easy to remember this for potential, but it's also going to apply to the third type of energy that we'll talk about today. So this is the reason why I introduce it here. I also want to introduce the fact that potential energy can also be in a flow. If I convert the mass to a flow, I can say m dot gz, where m is the mass flow rate. Let's do another brief example problem. Let's say that we had 1 liter of water at a position of 10 meters above the ground. Once again, we have to convert liters to mass. So 1 liter is equal to 1 kilogram by the same set of conversions that I showed above. And m times g, so 1 kilogram times 9.81 meters per second squared times z, 10 meters above the ground. I need to say that ground is reference, times 10 is equal to 98 joules. Not that much energy at all. The third type of energy, which is a little bit more nebulous, is the internal energy. And in this class, I'm going to define this to be the umbrella term for all other types of chemical energy. So I always think back to my organic chemistry class. I remember I had a professor who really loved theatrics, and we were talking about energy that could be stored in bonds, like the wagging or the scissoring or all the different kinds of molecular motions relative to each other that energy could be manifest itself. This is what internal energy is referring to. Like I said, it's just everything else. We're not going to get super bogged down in the details. We're chemical engineers after all. We're not chemists. And we're not going to be focused on vibrational, translational, and potential energy of individual molecules. So kinetic and potential energy, we're going to think about in the macro sense. And internal energy, we're just going to roll into this one term. And as chemical engineers, we are most focused on chemical energy. And we're going to spend most of our time talking about this. So we'll discuss this in much more detail as the semester goes on. But for our purposes, by the way, internal energy, the variable name is U. But for many chemical processes, U is going to be much greater, or delta U, so this is the change in internal energy, is much greater than the change in kinetic energy or the change in potential energy. And for that reason, this is the one that we are most concerned about. So the two key points I wanted to make sure that I touch on in internal energy is that there is no equation for it. And because of that, it must be measured relative to a reference state. So I have to arbitrarily define a state at which I say a certain chemical has zero internal energy, and then measure a change in internal energy from that reference state to the state that I'm currently analyzing. These are going to be the three types of energy that we discuss. Moving on, let's next talk about the two methods of energy transfer. The first method of energy transfer that we'll discuss in this class is heat. And heat is the energy that flows due to a result of a difference in temperature. And the thing to remember about heat is that it always flows from hot to cold. And I'm going to put the words hot and cold in quotation marks because these are also relative terms. One of my favorite funny stories that has to do with heat has to do with my high school days. I went to high school in Michigan, and one day in January, it was very cold outside, freezing cold outside, and the heat system in the school broke. So we were allowed to wear our winter coats and our parkas into the classroom. And I went into my biology class, and my friend Chris was sitting in his desk with one of those ice packs that you put in your lunch on his face. And I said, "Chris, what are you doing?" And he says, I'm warming my face up. And it's funny because in this definition, heat flowing from hot to cold, when you measure relative to his face, I'm sure it was hyperbole, but the freezing cold ice pack was hotter than the ambient temperature. Therefore, heat was actually flowing from that ice pack to the ambient temperature, not the other way around. So heat is going to be one of the main ways that we can get energy to flow, and our symbol for heat is going to be Q, or for a flow of heat, Q dot. The second form of energy transfer is work, and work is energy flowing due to any driving force that is not a temperature difference. So when I think of work, I think of those strongman competitions where they're pushing a car or picking up a big heavy rock or something. These are all energy flows due to a driving force that is not a temperature difference. The symbol for work is W, or W dot for a flow of work. So to close out this video, I just want to mention the convention that we'll have as chemical engineers. So CHE convention is that heat and work are positive if they are done to the system. So the convention is Q and W are positive if done to the system. So this can oftentimes be confusing, especially to those who have studied mechanical engineering at any point. In the mechanical engineering convention, they describe work as positive if done by the system. So you have to be very careful in defining what exactly your system is when you're defining what the sign of Q and W are. So by extension, then Q and W are negative if done by the system. So when you're defining these things, once again, you have to be very careful about what your system is. You have to call the system the right thing, and then you can define what Q and W are, positive or negative. That'll do it for this video. In the next video, I will discuss the energy balance for closed and open systems.